you know, it's a project where a lot of Germans in, so we try to keep the schedule. Yeah. Although this is now the speech recognition part, so it might be that we try to mess up this whole thing now. Yeah. So let's see what happens. Okay. What we are reporting now is work on ASR in the context of aging. 3 people will present. Number 1, it's me. Then Puyang will say something on speaker age mismatches, if speaker age mismatches model age, and then we will also have some slides on the problem if we could predict the future of a speaker in terms of models. Yeah. So first, let's start with the baseline system. The point is, before we started this project here, we didn't know exactly which type of data we have to deal with, so we decided to go for a very robust system that we can adapt quickly to different setups. And we also knew that we have non-native speakers potentially, and it could be variation of channels and these kind of things. So we decided to go for a broadcast news system because it's giving all these different conditions and you can quickly adapt them to different corpora. So we rebuilt the total system. So we have a new feature extraction, new training, new decoding. It's all based on given JHU, HDK, Hub4 recipes. It's a 1-pass trigram system with crossword triphones. It's running in 7 times real time on the Hub4 development 96 task and is giving their state-of-the-art baseline performance. What we also did is, to show this here, we made sure that we don't have problems in the decoding with the pruning. So we made experiments that we are running really on a safe point with respect to the beamwidth of the decoder. Before I continue, let's define some terminology because we have several projects here in the workshop and people report all the time on error rates, but sometimes you don't know what people are talking about. So number 1 is when we talk about error rates throughout these presentations, the next 3 ones, it's word error. Yeah. Number 2, when we talk about likelihoods or log probabilities or so, it's all the time log posterior probability or posterior probability. So it's including acoustic model and language model. Yeah. MLR adaptation is a well-known notion. When we talk about adaptation, we mean supervised adaptation because we do these age experiments, so we have a development set where we can make a supervised adaptation too. Yeah? An age chunk is just a piece of data which contains speaker data which have a similar age, so speakers which have a similar age. Yeah? And we have partitioned this, the data into, in principle, into 6 chunks from young to old. Yeah? Then there is a notion which is random chunk. This means we take randomly data from different ages and mix them. Yeah? So the random chunks contains data just from different ages of a speaker or from different speakers and so on. Okay? Then we have 3 different adaptation types. We have the age adaptation versus the speaker adaptation versus the gender adaptation. Age adaptation means we adapt to a certain age. Speaker adaptation means we adapt to all the data of a certain speaker. Gender adaptation means we adapt to all the data of a certain gender, male or female. Okay? And the final notion that we use is model age. This means this is the average age of the data. It's the average age of the speakers that provide the data for the certain age chunk. Yeah? So it's clear, I would say. Good. The British Queen Corpus, Elmar said already a lot about this, and I will also not play sound files, so we have done this already. This is a division in dev and eval. So we have these 6 age chunks from 26 to 31 is one chunk. The last one is from 72 to 76. You see that the perplexities are, well, okay, yeah, and there's not a high variability in the perplexities. The number of words is almost equal. It was a big problem to, sort the data in a way that you have the same amount of words, yeah? And the same on the eval data. And you see that's comparable, also that the age chunks are comparable on the def and on the eval data. Good, I said already supervised MLR adaptation on the development set. Okay, first results. take the Hub4 models and decode on the queen and do nothing else. Just take the plain Hub4 models. Then we see in age 26 to 31, error rate almost 60, and it's going down to 42.
Excuse me, the age 26 to 31, that's the training data that you use to create this model?
No. We use the broadcast news training data, created a model, and tested on the data of age 26 to 31.
In the Florida data?
No, we are on the queen. The queen.
Oh, the queen.
The queen. Yeah. Yeah. So take data from the queen. So she's 26 to 31 years old, and test on these data. Yeah.
But she's not involved in the training or anything.
Not in this thing. No. No. Yeah.
But she proves with age.
Yeah. She improves with age. Yeah. This is something which Elmar didn't like because it said it must be a U. It must go that. Yeah? So, but okay, that's what we see. Yeah?
That could be the language model.
Yeah, but we see from the perplexities that there's no big change. Yeah? Okay, you see for the first chunk. For the first chunk, wait, go back. Here you see that the perplexity is high, but then it's almost stable. Yeah? So.
It depends on how the models that you have created, from these resource management.
This is one interpretation. The point is in the broadcast news, if you look at the distribution of ages in the broadcast news, I mean, we don't really have it, yeah? But you know that the speakers are around 40, 50, so they should perform best also, yeah, on these data. And we see that also in the Florida data later, yeah? Okay?
Go back one more time. Thank you.
Okay. Next, we do a supervised adaptation to the age chunk 26 to 31, for example. Yeah? And this is still a test on the same training data. We test on the training data. It's just an experiment. You see it considerably improves to 34.22%. It's not a surprise because it's testing on training. Okay? But you see it's overall ages improving, so and you get 40% on that. Okay? I will show later experiments on the eval data.
So you're training on her, so you're doing both speaker adaptation and age adaptation.
Yes, I'm coming to that now.
What? Testing and training.
Yeah. The next thing is, yeah. Wait. I repeat what I'm saying again. Speaker adaptation means I'm taking all the data from the queen that I have on the dev corpus, overall, adapting. It's speaker adaptation. That's why it's called speaker adaptation.
So
okay?
So it's once and for all.
Yeah.
In other words, the system is the same.
Exactly. For all, it's the same system.
Yes,
yeah.
In fact, let's be more specific. The first column are the broadcast news language acoustic models. And the column that you can see now are the same models adapted to all the data in the 6 age categories, including the category on which the result is being produced.
Okay. Now comes the interesting part, because now we do age adaptation. So we adapt to the age 26 to 31. Still on training data, still test on training data. Yeah? Then you see, and this is an interesting part, if you see an improvement here, because then you know that there's some information in the age. And you see overall it's going down from 28% to 19%. And you see it is going down for each age category. So there is information. Yeah? Okay.
Do you know that this would not happen if you picked 7 random groups?
I'm coming to that. Just wait 1 second. Now we go for random.
Is it possible there is another factor like the recording equipment?
When I talk about age, wait, it's important. When I talk about age, I mean not the age of the vocal tract of the speaker. It could also be just the microphone, these kind of things. Yeah. But we have some answers to that. Just wait. The random subset adaptation, this means just take out of all the ages randomly data, but have the same size of adaptation data like for the supervised age adaptation, just to make it comparable. Okay? You see?
How can that be comparable when you're training on different data than you're testing on?
I show on eval. Yeah? It's of course, it's in that sense,
In the rightmost column, you're testing on the same data that
Yes.
you're trained on,
yes.
and in the second column, you're not. So they're not common.
You're right. No. It's the point is what we want to analyze here is what is happening if you do take just random data. Yeah. Okay. Let's come to the eval to the eval slide. Then you see it better, I would say. Yeah. If you do speaker and age adaptation combined, then you arrive at the best result. But this is test on training. This is just an experiment to see what happens. Yeah. Now let's talk. Yes, it's a cascade of 2 transforms. Yeah, first speaker and then age adaptation. You see this again, the performance on the development data, now just as a graph over all ages. Yeah. Now let's come to the very important test, which is now use training on hub 4, adapt on the development data of the queen, and test on evaluation data. Yeah. So this means we have now a different test set than as adaptation set. Okay. This is the honest test now. Okay?
Well, hold on. This is an honest test. How does it come to be honest?
Because you have separated dev and eval.
Separated by what mechanism?
Just different sets of data. Just taking out, 50-50. You just take out the utterances, yeah, for dev and have another set.
From different broadcasts, right?
No. The hub 4 training data is all the time the same.
No, I'm talking about the Queen's broadcast.
Yes, it's from, yeah.
You're not going to test on the same broadcast that you're training on.
No. Yeah?
So when you do when you separate it, you don't take part of her speech. You take a speech in 19.
Yes. So we have an utterance. We have, for example, the Christmas speech, yeah, of the Queen, yeah, for 1 year, yeah, and then you have the Christmas speech for the Queen for another year. So one is going in dev and one is going into the eval. Yeah.
The only common thing is that they're both in the age range, let's say 31 to 39.
Exactly.
So some of them are in dev,
Yes.
some of them are in eval.
Yeah.
So it sounds like you're not cheating. Go ahead.
Exactly.
Sounds
Nice that you say that.
It sounds
Okay.
like every effort has been made not to cheat.
Well, that's going too far.
Well, I would say every effort that you can run within 6 weeks.
I see.
Yeah.
There was
Okay.
another question here. Maybe I'll
Hey.
just touch on each effort.
Okay.
Again, we have
So we can conclude that those border rates are correlated with the year that the data was recorded, not the age, right?
could be.
Yes, could be. Yeah. That's at least a conclusion that we can draw. Yeah. You're right. Okay.
By the way, one of the questions that I've not been asking is, how is this data recorded?
This is a good question.
We don't know too much about that. I have a book on BBC technology, and there seems to have been 3 changes in microphones, but continuous improvement.
But the recording medium itself.
Up to the 50s and 60s, it was a tape, and then it was later on put from the tape onto digital stuff, and probably starting in the mid-70s, it was digitally recorded. But we don't. We tried. I wrote to BBC, and they said, "Sorry, we have no data on that."
But you can hear actually, you hear the early years, you can hear the wobble of the real recording.
I think we need to find a BBC sound engineer somewhere.
There is a.
No.
I have a book of that size about the BBC technology.
So for the early years, you could hear the wobble, but surely that has nothing to do with performance that we see here.
I don't think so, no.
No, this is a mixture of microphone and everything. But yeah. What do you see here?
Although when you go to the experiments with age classification, actually that may be something that, because that actually sounds very similar to really the way people speak when they age.
And I think this is also the reason why we always try to verify whatever we find in these longitudinal data on a database, that we kept the content constant, we kept the channel constant, and we varied over many speakers. So the University of Florida database does exactly that.
You know,
They
I guess
speak.
the only thing I'm thinking is, you know, the top two rows here have the wobble in them. They have higher error rate, but there's probably no connection between those two things, right?
I think there's different things that have to do with the data.
Yes,
You
yes,
look
yes.
at the-
Yeah. So, okay, on the eval, similar error rate. So you take the Hub4 models, you don't do anything. Take the same model, go over the different ages, and take the error rate. Now, we still have done supervised adaptation on a def set, which is another set than these test data here. Yeah, so it's the first honest test. You see, it's still going down significantly, but it's speaker adaptation. It's not a surprise. Okay. Age adaptation. That's the next step. So we have to compare this column now to this column now. You see, we still see an improvement. It's not that revolutionary anymore, but it's also, I would say, clear because we are working on
Is
a
there no
evaluation.
speaker adaptation in that line?
No, in this one there's no speaker adaptation, not yet. So it's just direct adaptation to Queen at age 2631. So it's like a speaker adaptation to a speaker of a certain age, say it like that way. Yeah. So yeah,
So it is speaker adaptation.
it is age adaptation because it's a speaker at a certain age. But in a certain sense, you can also say it's speaker adaptation. Yeah, you are right. If you treat the person at different ages as different speakers, you can also say speaker adaptation. Yeah, yeah. So it's partly channel adaptation. Yes. Yeah.
No, George is right. You know, the first
Yeah.
two rows, you're right. There's a lot of wobble, and
Yeah.
this is doing channel adaptation
Yes.
to that.
Yes.
Oh, but surely there's nothing to do, no connection to each other.
Okay.
You may
Then-
very well think so.
Then do the stuff now with the random subset. Just this is now the honest test with the random data. Yeah, because there's no difference in mismatch anymore with respect to the previous one. You see, random choice is doing worse, and that's also clear because you do basically a broad speaker adaptation over all the ages of the speaker, but you have less adaptation data. Yeah. Speaker adaptation, this row, yeah, these models followed by age adaptation. Yeah, first adapt to the total speaker over all ages, and then adapt to the speaker at a special age. That's the last column, exactly. Best result. Okay. If you look at this in a graphical way, then you see it's going down over the ages, and you see improvements from no adapt over random over speaker over age over speaker plus age adaptation. Okay? On the eval data. So that's the honest test. Okay, this was the queen, and now we can say it's one speaker. So we cannot draw any conclusion because it's just one speaker. Yeah? So the next question would be, what would happen if we do this now in a speaker independent scenario? Yeah?
I should repeat what George is saying. We cannot draw strong conclusions both because it's only one speaker and because we could very well be just compensating for the recording conditions.
You're right. Yeah, it's clear.
It's fair.
Yeah,
It's fair. Yeah,
very well
it's fair.
doing it, and at
Yeah,
this point,
you're right. You're right.
take the position that
At this point, you're right. Yeah. Now take another corpus. This is the UFVAD. I just call it Florida corpus. Yeah, because it's coming from University of Florida, from the vocal aging department, I assume. That database. So, what is important here for adaptation experiments? It's number one is read speech. It is read speech because all the people have the same text. So we have the language model problem out. It's one and the same microphone all the time. So we have the channel problem out, microphone problem out. Yeah? It's a uniform distribution of age chunks over male and female again. So it's a nice database to make these experiments on. So we just let speakers of different ages just read one and the same text, basically. Yeah? And we have enough data at least to do adaptation work, 25,000 male words, 25,000 female words. Okay? So for those who are not familiar with these set sizes, it's approximately the size that you have on Hub 4 development and evaluation test data. Yeah? So experiments are speaker independent, and we focus here for this presentation on female because you see the same in male and we don't need to repeat this. Yeah? So whole thing again. So now do the same experiment as done before with the queen on the development test. Yeah? So here you see this is a cheating experiment because we test on the training data, on the adaptation data. Here you see this nice, number one, this nice U-curve that Elmar wanted to have. Yeah? So, okay. You see it's going down the error rate for no adapted models, and it's going up when the age increases. With a random subset adaptation, this is basically gender, no. Is this gender? Yeah, no. This is gender adaptation, basically. Also, the random subset is just a smaller subset of the gender. The blue one here is the real gender adaptation. So you see the difference from gender independent to gender dependent, and it's also a kind of channel compensation between the Hub 4 and the Florida corpus. Yeah? This is Florida. Speaker independent.
So the top blue line again is just your vanilla broadcast news model, and then the cyan light blue line is the broadcast news models adapted to all the
male
all the female speech.
Yeah?
So again, it could be gender, it could also be the recording conditions.
Yes, exactly. That's what I say.
Yeah, but
It's
here the recording conditions are the same.
No, they're the same, but they may be different from broadcast news.
because we start with broadcast news models.
But it wouldn't show an age.
Yeah, there's
Yep.
the age component.
Yeah.
I'm saying, no, it changes in Florida also.
You know, but this is data collected over there. Right. This is data collected. This is only people age, not the machine. Because they collected data over a period of 2 years.
Peter, what was the cheating part?
The cheating part is,
You said it was a cheating experiment.
the cheating part is that we are testing on the same set that we have adapted on. Okay?
But you're going to show us non-cheating, right?
Hmm?
So why are you showing us the cheating part?
Because it helps a bit in understanding the whole scenario. That's for analysis. Okay? So you see, here you see that there's something in with age, yeah, because you see this jump from gender adaptation to age adaptation, yeah, and you see gender and age adaptation is improving. Now let's go for the non-cheating part. This is a non-cheating experiment, the real test, yeah. No adaptation. Then we have the gender adaptation. You see for the young speakers, a lot is changing here. Yeah? For the elderly people, you see also considerable improvement. Now you go from gender adaptation to age adaptation. Yeah? Okay? So this means we adapt to age, say 20 to 30, for example, here, on a development corpus, and then test on speakers with the same age on the evaluation corpus, but the speakers are different. Okay? Yeah? And the last line, the black one, is gender plus age adaptation.
I'm confused. It's all on female data, so isn't it gender plus age and age the same?
No.
The age includes male?
No.
No adapt. Includes mouse.
Age adaptation includes already adaptation to female speakers of the same age.
So maybe let me say it differently. So that let me see if I can compare three lines: the dark blue line on top, the light blue line in the middle, and the green line at the bottom. So the dark blue line is a mixed gender acoustic model on broadcast news.
Yes.
Then the light blue line says adapt this to the Florida female data.
Yes.
So you may have done some gender adaptation because a gender-independent model is adapted.
And corpus mismatch.
But you may have also adapted to the recording conditions
Yes.
that were used in the Florida data. Now the green part says, oh, use only a subset of that adaptation data. Don't use all the females. Use only the females in the group that the test speaker is in.
Yes.
The test speaker is a separate speaker. So you're actually adapting on less data.
Yes.
much less, in fact, maybe a sixth of the data or something.
1/6 of the data.
More specific adaptation.
But you're getting more gain, so it means you gain more. So of course, if you had more data, you'd learn the channel better because it's a different channel.
Yeah.
You lose a lot of that, and yet overall you gain more.
Yes.
So,
So
are you willing to claim that age is the bigger factor?
Well, essentially,
Okay.
I would say on this set of data, yeah, and especially on this part of the curves, I would say yes, it's the age, yeah.
But aren't the three curves to compare the dark blue, the light blue, and the black?
Yeah, the black is just a cascaded version. So the black just says do light blue followed by green.
That's brown.
All right, brown. Yes, it's cascaded, and it shows you the value, the added values of adding age.
Yeah, refining further the
Yes.
adaptation.
Yes.
So the step from the blue to the green one shows you the added value of adding age.
No, it shows that because as Steve said, you have less training data, but it's a different kind of, it's less, but it's age targeted.
It's less, but it's age matched.
Yes.
And the results are equivocal. Or better.
You mean between the green and the black?
No, between the green and the blue, the light blue.
Okay. On the low end, it looks fairly different.
Yeah, on the high end it's worse. So, but the interesting thing is when you compare the light blue with the black, it definitely is an improvement.
Yes. Yes.
Yes.
That's unequivocal. But we don't know the standard deviations. I mean, slightly either of those. But anyhow.
The point is we didn't have the time to do. Yeah. Okay. So this is basically the key findings that we have. Then we have made one more experiment because what we do here is in the test we already assume that we know how old the speakers are. Yes, because we have defined age chunks. Okay. So, but what is it now if we don't know how old the speakers are? Yeah. So what we do is, this is by the way the table for that. What we do it, and you see it's nothing deleted. We take 6 models and run them competitively on each utterance. Take the model which has the best score or the best likelihood. Yeah, it's like with vocal tract normalization. Yeah, and take this one then as the recognizer output. Yeah, it's an unsupervised method, yeah, of selecting age, the right age model. And we arrive at 43.33%, which is the same as we would know the age. That is the right one. Okay.
Can I ask, maybe, these are ordinary state-of-the-art recognizers, right?
Yes.
Consequently, they have nothing to do with the previous lectures that you gave us. In other
No.
words,
Has nothing to do with DMC. No.
Or anything,
No.
vocal tract.
Yep. Yeah, exactly.
Yeah, it has
Yep.
nothing to do with that.
Yeah.
There is a value on having, I guess you guys can give this slide. There is a value on having the prior work done because, I mean, he's using 3 groups of age, you know, young, old, whatever. I mean, the question, why 3, why not 4, why not 5, and how do you break out the groups, you know? Based on their data now, we can go back and see what is the right...
Yeah, but they could have done something else. They could have tried their models to estimate the age and then segregate it for that age and create a language.
That's running.
Fred, this experiment is at the moment in the queue. Yeah? Yeah, so, okay. This was my part, now Puyang is coming. And I promise we mess up the time, and we did. So.
Yeah, like Peter introduced, I'm going to talk about the what happens if the speaker age is different from the model age. Namely, the model is adapted to a different age group as the speaker's own. So I'm going to start with one very interesting experiment that we did. So here we have 6 models. so adapted to each of the 6 age chunks. And what Peter did is going through the test corpus. I'm sorry. Going through the test corpus, utterance by utterance, and simply pick the model that gives the best likelihood. So here's another experiment. What if we decode this group of data using the 6 different models? And here is the per frame log probability that we get. As you can see, that the best probability appear when the adaptation is done to the same age period. And if you inspect more carefully, it's actually a monotonic trend. So you go away from the diagonal, the likelihood gets worse.
Isn't the validated?
Yeah, it's in the validation data. But it's on the queen.
So the model is adapted to some speech in the 26 to 31 year age group.
Yeah.
Okay, and then that model is used to evaluate the likelihood of the test.
Around 26 to 31.
And the test data happens to be in the 26 to 31 age group, then you get a likelihood of 63.2 bias
Yes.
per frame. If you had adapted the models to a different age group, 40 to 46, then your test data log likelihood for the 26 to 31 speech would have been minus 64.
Yeah. Yeah. So if you look at, okay, you can look at the rest of the table. So the trend is very clear. And it is almost always that, actually the best performance always appear at the diagonal. And the monotonic trend is also very obvious. There are a few exceptions, but the trend is very clear. So in this table, the darker the number gets, the worse the likelihood is. So, and we also made a, so this is actually, we actually summarized what we have found in this table with a law, the posterior probability, decreased monotonically with age distance between model age and speaker age. So,
Which could not be age, it could be channel or anything.
yeah, because this is on the queen. And here's a plot that we made. So it looks like somehow looks like a butterfly, so we call it a butterfly plot. So each color represents the age group. I'm sorry. Each color represents the age group. So basically, it is a per year analysis of the table that we've shown before. So each curve is 1 year. The x coordinate is the difference between the model age and the speaker age. And the y-axis is a decrease of log likelihood. So all the likelihood is subtracted by the group from group result. So it's a per speaker analysis of the experiment that we ran before. As you can see that as you go away from the diagonal, the age distance increases, the log likelihood decreases. Okay, we have a few outliers, but I think the trend is very clear. Okay, continue. So Sanjeev also suggested that we should also look at the word error rate. So here is the first row. So as we expected, best word error rate appeared when the adaptation is done to the same age period. So you go away from the diagonal, the error rate decreases monotonically. And the rest of the table, it is still very clear. Because the red numbers have the optimal word error rate. The darker it gets, the worse the error rate gets. Okay, this will be the second law. So the error rate increases monotonically with age distance between model age and speaker age. Okay.
Isn't that true for almost any kind of adaptation?
No, the fact that it's monotonic with age is actually informative, right?
I don't understand why.
Yeah, because if it was the recording condition, one would believe it's more random.
I see.
One would believe. Yeah,
The point is the monotonic part.
Yeah.
That is decrease is clear, but
right.
it's monotonic.
It's the monotonic part that's
And there's
surprising.
something else which was somewhat surprising because we thought that if the recording technology is getting better, then we would see a trend in one direction but not in the other. But this holds across.
Yeah.
Maybe it's different effects, but that's
That's the lesser thing, yeah.
So okay, this will be the butterfly plot for word error rate. Does not look as nice, but the trend is still the same. We have outliers, but it's still that going away from the true age, the word error rate increases. So let's go to the next slide. So this one we also we're quite aware for the Queen experiment. There's a big channel issue over here. So we tried this on the Florida data corpus. So this is experiment that we done when the adaptation is female deaf, cheating experiment, decoding. Is cross-decoding on the same female deaf. As you can see here, the trend is the same.
So one can think, sorry, of the likelihood score as a phone-dependent score, you know, to describe age difference.
Yeah, it's an average.
That's what's happening in an unsupervised way.
Yeah, yeah.
You can collect whatever statistics you want, actually. And likelihood is just one number.
Yes, there would be other.
So except for this experiment, there are no same speakers between the adaptation data and the test data. So given the tough setup as it is and the speaker variation, we're very surprised to see a very similar result over here. So if you go away from the diagonal, the results actually gets worse. So this is the result of per frame log probability. And we also have the results for likelihood. Okay. So you probably noticed that sometimes the best error is not at the diagonal. Sorry, this is on the female development data. Okay, this is on evaluation data, the log likelihood. Okay. You could just inspect this table by looking at the colors and darkness. So the trend are all the same. So if you inspect this table more carefully, sometimes the best error rate is not always at the diagonal. We found it very interesting. Actually, Stephen is going to talk more about this. But
why is it in red?
it is the diagonal, which is
the red is diagonal.
diagonal.
That was the best.
Well, for the queen, it was the best. It's a,
Oh,
yeah, I'm sorry. I should have explained.
But well, I don't know what is white and what is gray.
Yeah. Okay, we also have this, I think, much nicer butterfly plot. It's not symmetric. It's not balanced. It's a little bit lopsided. So, so probably if you go to adapt to an older model, you'll pay a higher price. It's probably more risky, actually. Stephen is going to say more about it. I'm going to skip this slide. So we also did the correlation experiment. So basically, it is a correlation experiment on this graph. So we have the word error rate correlate with the biological age and perceived age. You see that if we done correlation experiment with perceived age, we get a very big improvement. We also have the log likelihood, and this is the results on the queen. So, and we actually go back to the sound files on the Florida corpus, and this is the per speaker analysis correlation. As you can see that we have quite a few outliers over here. So actually, they were not actually reading speech, maybe just some uncooperative speakers. Okay, so with that, I think that's the end of my talk. I'm going to introduce Stephen to continue our talk on speech recognition work that we've done during this project.
All right, so I'm going to pretty much pick up exactly where Puyang left off. And he showed you this plot, or this matrix, where the diagonal doesn't seem to have the lowest results. In fact, it seems maybe these three numbers, say off the diagonal, slightly below, seem to produce the best word error rates in the recognition. And so let's take a look at the core. Sorry, these three?
33.
And, yeah.
One up, even one more.
Oh, well, this one is too, yes. Not quite as significant, but yeah.
Last four diagonal tails, the best one is one to the left.
Yes,
Yes, exactly.
but the trace is the same.
Yeah, it's always one to the left.
It's not noisy, it's a shift, yeah.
So it's, sorry, this one,
I thought that's noisy.
that one, that one, and that one.
Yeah, okay.
All right. And so I guess we can tell a short anecdote about this. There's the corresponding plot, and once upon a time there was a grad student working for Peter, and he looked at this plot and said, you know, Peter, the minimum isn't exactly right in the center where the difference between the age adaptation and the difference between the age adaptation and the test speaker is actually at 0. The minimum seems to come here, as in the minimum word error rate. And Peter says, oh, well, that's just noise, like he just said a second ago. However, keep in mind these grad students are all overworked and underpaid, et cetera, and everything. So Peter decides to give him yet another task to do and to explore this effect. And it turns out, indeed, that the Su effect, named after Puyang, Peter's the grad student working for Peter. What we have is that both the Bayerlein-Kudampur law and the Kudampur-Bayerlein law show that speaker-independent data, there's a left shift in age. So perhaps this might suggest Though I can't make that conclusion. It's just pure speculation at this point. Perhaps that might suggest we should adapt older models on slightly younger data. So basically, I guess that leads me to an outline of my talk. I just explained the Sioux effect, and I guess also for the next couple of minutes, most things I'm going to say are pure speculation. I'm not actually drawing any conclusions, but these are observations that we should probably shine a light upon, maybe see if we can do some future work on. So the next thing I'm going to talk about is MLR prediction. MLR, we all know it's the transform that is created to do speaker adaptation. It's one of the ways to do speaker adaptation. And so we're going to take a look at MLR prediction, and we want to maybe see if we can extrapolate future MLR matrices of a speaker. And to do so, we have a couple of experiments that we ran, and I'll show you some of those results. A little bit of just motivation about what I'm going to say here. It's, well, what if we could predict the future of an MLR? We can do a number of things that have also been proposed in the past. In terms of defense, perhaps we can predict what a person will sound like in 5 years, given what they sound like right now. And then in terms of medical, maybe we can predict how a person also is supposed to sound, a healthy person is supposed to sound 5 years from now or 10 years from now. And if their speaking actually differs, then perhaps there's something we should investigate upon. And finally, of course, there's the society and commercial application to this idea where if we can build ASR systems for elderly people that can actually age together with their users. I mean, the speech recognition will age with the users, not the systems. So what we have is an interpolated age. I just said that we were looking perhaps to extrapolate what a person might sound like given a recording now. Maybe we can extrapolate what they'll sound like 5 or 10 years from now. And so, well, before we can extrapolate, of course, we need to be able to interpolate. And so we wanted to take a look at this. So if we adapt to age, if we adapt a speaker on a test utterance, if we adapt the speaker to his own age group, we get an error rate of 36.65. We get these falling error rates, yeah. And but if we just adapt to a random chunk, then we get obviously clearly a higher error rate. So what happens if we don't actually have data for this particular age group? Suppose we have a speaker who is obviously between the age of 31 and 39. However, all we have is data for, say, a little younger, from a group a little younger than he is, or her, and data from a group that's older than the current speaker. And so we try this, and we want to see if we adapt to the neighboring chunks of data, given that current speaker, neighboring age chunks, can we actually achieve similar error rates as if we adapted on that exact chunk? And I guess we see that it actually works. If we only adapt to a younger, if we adapt to younger or older, we get the results seen here and there. However, with this interpolation, perhaps we can say that well, these error rates are very similar to if we just adapted to the exact age group of the speaker in this test utterance. So,
are you keeping the amount of adaptation data the same?
Yes, the amount of adaptation data is the same over all the adaptation. So I believe it would be half and half of the two. And this perhaps suggests maybe the possibility of within neighboring age chunks, we can say this might suggest a first order interpolation is possible in this fashion.
Right now, this is data interpolation. You take data from the two neighboring groups and mix them and adapt to that.
Yes. And we just take two chunks. If the speaker is here at this age region, and we just take the neighboring chunks of the data, adapt to it, and then test again on that age chunk, and this is the error rate we get. So yes, yeah, and so for now we can say interpolation seems to be, have potential. And yes, either one individually at this point. Yeah, we must reserve judgment, I guess, because this is all on the Queen single speaker. You know, we haven't expanded, but this is what we have come up with so far. Now the next idea, moving on to the second part, is the MLR matrix. Now this is a sort of a heat map of the MLR matrix, 39 by 39. This here would be the 0, 0 element, and this will be 39, 39 in terms of the indices. And so a couple of things. This is just the adaptation over all the ages of the Queen. So this is all the ages of the Queen. Just put it all in one big chunk, super chunk, and then adapt to it.
So is this only mean adaptation?
Sorry?
Is this only mean adaptation?
Yes, that's true. Yes.
Of the means of the Gauss, that's what I mean.
This means of the Gauss.
And it is constrained?
It's just
MLR.
It is constrained MLR?
No, it's model
plain
No,
MLR. Plain MLR.
Plain.
Yeah.
What I mean is that you're using a single matrix for all the Gaussians. You don't have per component.
It's
Gaussian.
one global matrix. Yes.
All right.
Single global matrix.
No, but there are various.
Yep.
Yeah. I guess, we just explored one of the ways, just to see what would happen. And I guess just a couple of things to note, really. A lot of the activity in terms of this this matrix is localized to, I guess, the rightmost 13 dimensions and the top, and of those, the topmost 13 dimensions. And so what we also did was to do it for all 6 different age chunks that we have of the Queen, and these are each the separate MLR matrices, all plotted side by side. So right now, what we've got, and you see the same trends. You know, the rightmost, topmost 13 by 13 dimensions seem to have most of the activity. So what we could do now is, since we have, in the previous slide, we have all over all the ages, and now we have over the MLR matrix for all the ages. And here we have the MLR matrices for just specific age chunks. So what might be an idea to do is to subtract out the one with all the ages, like subtract out the marginalized ages from each of these, and we can see if there is actually some time, age, channel, some temporal dependent information in these MLR matrices. And indeed, that is what seems to come up. These are, again, the results that result from this subtraction. And I guess now the most important thing to note would be just this last column here, what would it be? The 39th column and the first 13 dimensions, which in our setup would be the second, or it would be the energy component of our features, and yes, the energy component, and perhaps because of the 39th dimension, the second derivative of this. So that is what we have, and so there's obviously a lot of further work to be done. We only came up with these results rather recently, like last night or 2 nights ago. However, we really would like to understand what is going on in these plots, and maybe in such a way we can develop new methods to predict MLR future, given a few ones in the past. Maybe there's some way to interpolate and extrapolate given such information. However, so all I have right now are the plots that are generated, and hopefully I'd really like to see if we can do something about these transforms and adaptations. With that is, I think it's back to Elmar. Yeah, the left one is next.
Okay, it's time to round up our presentation. Let me start with a couple open questions that we had before the workshop. So the first one was, can we classify the age of a speaker with any kind of robustly extractable information from the acoustic signal? And I think after having looked at the Florida database and keeping in mind that the age classification results of the humans were actually the average of 40 judgments, and we weren't that much worse, I would say, unfortunately we didn't have in time the data of individual raters. So, but I think, with that fact that we're comparing a mean of 40 judges with one classification algorithm, I would say we're approaching the range of humans in the classification performance.
But humans are no good at this problem.
They're not too bad. I mean, if the perceived age and the actual age has a correlation of 0.95, it's not.
About pegging age to within 9 years based on 10 seconds of speech.
That's not too bad.
Well, I am judging by myself. I certainly judged the Queen. When you gave these two extremes or whatever, I thought it was the other way around. So at least I'm no good at it.
I guess I have to object a little bit to saying that you compare human performance. Humans are actually quite bad, and what you're trying to do is to see, you're trying to use humans to get a bit of a handle on how well, what's possible. So you combine 40 humans, and of course, the reason that the slope is less than what it should be, of course, is because a lot of humans, you have random noise in there, so it's going to pull it back to closer to zero correlation, but you have to compensate for. That's not a problem. But I guess what I'm objecting to is talking about this as though it's human performance. Actually, humans are much worse. And what you're trying to do is find out what's possible, and to use humans as a window onto what's possible, and combining 40 of them to get to that point.
And you don't understand why I think humans are
well, if you take a human, the correlation could be visible.
But didn't he take
No, he took a panel of 40
I took 40 humans, and I think by taking the average over many.
But they were not trained, right?
No, but still, if you take the average of 40, you approach, you get a very good approximation.
Although people vote for George Bush.
Okay, I'm not going to get into that.
So the humans in this panel, they didn't do any training ahead of time? They just went to the web page and sat down?
No, wait. In the University of Florida, the people actually came into the lab. It was not a web page, so it was carefully selected. And we're comparing the University of Florida, our classification of the age, and our error of 11 years to the 9 years, which came from the average of 40 judgments. Okay? So, I think we're not doing too bad with the age classification.
Maybe you should say the range of best humans. Maybe you should say approaching the range of best humans.
No,
you mean like
much better.
But George is saying that even the best of humans, if you take any one individual human, their error is very large.
Yes.
It's just the humans as a collective.
Okay.
Mixture.
So
I think we're being
so I
modest.
don't know how to formulate it, so it's just exactly
It's probably a little bit modest to say we're approaching it.
Says what you...
So along those lines, are there people who are Olympic grade age judges in your view? or is there not much variance?
Well, I showed the variance in the test that we did on the web, and there was, people who seemed to be kind of random, and other people who were doing very, very good.
So there is some innate ability. There is some innate ability to
Yes,
test age.
absolutely, I would say so.
But how do you control that if it's not the same text? Because people have
What we have to do is go back.
Way to
What we have to do is go back to the guys who collected the Florida database and get the individual judgments, which I'm sure we will get, and then look at that.
Okay. Yeah, but again,
one other comment on this. You cannot, after the fact, go and find out who had the best score and then test it
again.
That's why you take
Yeah.
the average.
I think, I mean, it's a good thing to compare it with the average because the average really smoothes out individual stuff. And if you take the average is pretty good. Okay, so next question that was open. Can we find features that explain the change in the acoustic signal? I think we can say yes. The excitation parameter and the Maeda parameters show competitive performance. Better refined models are possible and should be done. They require more work and were out of the scope of the workshop. But, you know, questions like the inclusion of breathiness in the excitation would definitely improve the performance of these articulatory parameters. And also, so far, the excitation and the articulatory parameters have been optimized separately. So a combination of, in one step, optimizing the excitation and the transfer function will definitely show an improvement. Yeah, something like, I mean, we started out and say we will not, you know, will not restrict ourselves to articulatory parameters. We want to take any kind of features that we can get out of the signal to solve the task. So the question is, you know, anytime somebody does something, says, well, it's for a baseline use MFCCs, and they always turn out to be the best. So will they always be the best? Well, we can't really say that after the workshop. We use two databases. In the one database, the age was very, very highly correlated with the channel. In the other database, we took the channel out by using exactly one channel. And so, you know, in these channel, not mismatch of channel, MFCCs are always very good and hard to beat. And in the other stuff, you know, we're not that sure how much of the age that the MFCCs found, how much of that is the channel. So we don't know yet. Can we learn from longitudinal data? Yes, I think we can. Some trends came out clearer. We have a less lowering of the jaw, the P1, which is not, can be good explained with the aging process. We have the V-shaped F0 change with Cook that came out clear. Some potentially influencing factors came up with the interpretation of the results, and I believe that the V-shaped speech rate of the queen, that she speaks faster and then slower. I think the right side, when she hits 60, the slowing is probably due to aging, and there's other influencing factors of her speaking faster from 1952 to when she hit 60 in 76.
Excuse me, no. So this is interesting, but was this not also done for Cook?
We haven't done the speech rate analysis with Cook. It's just for two. Yeah, I know. Yeah.
Because it turned out you saw the same effect in both.
With Cook, it was not the same. I mean, it was more spontaneous speech. So it's more difficult to compare with the Queen. It was one setup. It was always the same. And so we could look at the speech rate and compare it directly. With the others, with the more spontaneous stuff, we have to really make a more detailed analysis. And it's just a question of the time that we had during the workshop. Is the age of the speaker relevant for speech recognition? I think we can definitely say yes. There is a clear relationship between the speaker's age and the word error rate. Also, yes, age mismatch between training and decoding is a problem. It leads to systematic increase of error. Age adaptation helps reduce these error rates. Can we learn from longitudinal data? Well, the preliminary results of, we haven't shown that we can extrapolate yet, but you know, if the extrapolation works, definitely the interpolation should work, and these results are new and very, very promising. Open questions after the workshop. What we have not done is combine the new model-based features with the MFCCs. We have shown that they show competitive results, but we haven't included them. So it's open whether the combination of MFCCs with model-based parameters will give improvement, in particular for data with multiple channels and many speakers. I think that's definitely a question that should be pursued. Can model-based parameters be applied for other tasks, like speaker recognition, emotion recognition, etc.? We believe definitely yes, it's a task on the list. Can we extrapolate speaker characteristics to the future, both with speaker and speech recognition? That's a very interesting idea. I think we should pursue it, and I think the interpolation results are promising. I think that's a way that we should definitely look, a thing that we should definitely look at. Can we find medically relevant deviations from the normal aging process? That's something that I'm very interested in. We're looking at data. We're going to collect data from people with starting mild cognitive impairment, and our colleagues in clinics, they say, some of them, they say, I listen to the guy, I know there's something going on. And, you know, I think if these people can do it, objective measurements will definitely be of a very, very great help. Can we utilize MRI and ultrasound imaging data? I think that these new imaging data can really help us, will form a new generation, so to speak, of base information from where to start these articulatory parameters. And I think if that is pursued, that we can make progress on that. Next steps after the workshop. Well, there's the dissemination of the data and the results. I'm very convinced that will be done. And on Friday morning, our group will sit down and see where will we publicize which subpart. Transfer results to larger cover of longitudinal data. The LDC is planning to collect the so-called Whitebeard database, I was told. Oh, graybeard. Sorry. My fault. Okay, graybeard. Anyway, collection of data from speakers that they had like 20 years ago. We have the same stuff in Germany. We also have speakers that we collected 20 years ago. We're also planning to do that. And I was talking right before the workshop with a guy in Munich who has AMAT data, so you know he puts sensors on the tongue and stuff, and he also has access to these people. And these data are 15 or 20 years old. So I think that's definitely a thing that will be of big interest to the scientific community. Apply developed models and features to secondary labels which may be available for larger corpora but have not been used. I think quite a few of the LDC corpora, there is side information about the speaker that we have not used so far, and we should. It's really worth it. And I had a nice discussion with Patrick Kenny on that. It's really worth looking at that. Investigate extrapolation problem for speech and speaker recognition. I think that's definitely a very promising thing. Let me summarize the presentation. We presented the data, both longitudinal and cross-sectional data. The human performance was not too bad. Well, it was actually quite good when you looked at the average of the people and correlation of up to 0.95. We looked at the source, and before the workshop, there was no implementation available to us. During the workshop, we implemented Stevens's excitation model. To our knowledge, is the first verification of the model on a larger data set. And I think just by looking at the correlation of the excitation signal with the age data, it's a quite amazing correlation just by looking at the excitation signal. With the filter, we found some quite interpretable change of articulatory parameters with age. The parameters we used, acoustic and prosodic parameters in addition to these articulatory parameters, which helped us to predict the age, and we could predict it with a mean error rate of up to less than 8 years. And with the speech recognition, we got nice improvements based on age information leading to extrapolating methods. Let me quickly go through some acknowledgements. I would like to thank all the people who participated in the test, which came from the University of Erlangen, the university in Wildau near Berlin, Saarland University, MIT, University of California in Berkeley, Johns Hopkins, and some participants of the CLSP summer school. Also thanks to the Computing Resource Center in Wildau for providing access to the high-performance computing system. We'd like to thank very much Andreas Andreu for his continuous support and participation. Also, Sanjeev, thank you for your continuous support and participation. And the whole CLSP team for their hospitality and commitment. James Hornsberger provided us with the Florida data, and on a very short notice came up here and gave a great talk. John Harrington provided us with the Cook and Queen data, and I had quite a few fruitful discussions before the workshop with him. Maureen Stone gave us a very inspiring talk and said she's willing to provide us with the image data for research after the workshop. And finally, Alan Gorin, I would like to thank him for his input and advice during the preparation of the workshop. So, as a team leader, I would also like to stress I've had a super team. I've had great, gifted grads and undergrad students. Most people didn't know each other before the workshop, and it took no time, and we were a really good harmonic team. It was a great time. I really enjoyed being here. Thanks a lot. And now Andreas is gonna.
Actually, I want to just say a few words. No, it's okay. I can show you, but it's okay. So for those who don't know what happened with this team, basically when the team was formed, 2 weeks, 7th week of May, which is really beginning June workshop, the team basically, half of the team decided not to show up. And so I think it's actually remarkable what has happened, and Elmar deserves an extra round of applause for really pulling this together, and that's the type of thing. By the way, I was just like the mom or the dad of the soccer team, takes cookies and helps with this and that, So, and these people didn't want to eat the cookies, they would rather be here working. I also want to say that I have participated in 2 other workshops as a full-time participant. This time I was just part-time, and the aging of the workshop is getting better and better and better. In that, actually, as time went on, I have found that the people actually, the undergraduate students, let's start with the undergraduate students, they're just remarkable. This is really amazing to see people coming in with no prior knowledge in the field and doing so well. So I'll just really.
So there should be a discussion.
Yep.
Questions? So discuss. So it seems that there was significantly more age effect in the longitudinal data than in the cross-sectional data. Is that right?
Well, there is definitely the speaker variability in the cross-sectional data. Now, let me say one thing, for instance.
I'm talking about the speaker recognition results.
Oh, the
speech recognition results seem to be more dramatic in the longitudinal data than in the cross-sectional data.
Point is, yes. Yeah.
And so I'm suspecting that some of those results are due to things other than aging.
In the longitudinal data, yes, because we assume that's the microphone, especially when the queen is young. I mean, that's very obvious. Yeah.
Well, another aspect may actually be the language.
Yes.
Yes.
Yeah.
Yes.
Absolutely.
Absolutely.
So, in fact, that would be my prime guess. Language is playing a factor.
Yeah, there were perplexity numbers.
Yeah. So that's why we
but it goes beyond perplexity. It goes
there could be some, for example, if, just as a simple example, if a particular set of words is used more frequently, then you're going to get more training data, more acoustic training data on those words that will have an impact on the error rate.
I would say we see with perplexity that for the young age it's really different than for the older ages of the queen. But what we don't see with perplexities is if the way she's speaking, and that would be my suspicion, is changing over time. So her way of pronouncing things, her way of making pauses and all these kind of things, they are changing. And that you never see with perplexities, of course. Yeah. And listening to the data and you hear these things, yes.
So the way a person speaks may change, and some of that may be due to aging, and some of it may be due to cultural or societal shifts, etc.
Yeah, this is what I subsumed under societal change.
So one of the conclusions of the project was also that it would be really, really important if we want to pursue this work on this aging, that we need a speaker-independent longitudinal corpus, where you have really a lot of speakers, but having the sound over a long period of time, which is of course difficult to get somehow. Yeah, but one could try to do something. Yeah.
Also, the government changes, and it's the government which writes her speech.
Yes. Yes.
That's not so true.
So George stole some of my thunder. I was going to ask whether, hate to suggest such a radical thing, but as a phonetician listened to it, I suspect there is drift in most speech over a period of 40 or 50 years. I mean, in my own family, dialects have changed, and they changed for various reasons. I can cite 3 different reasons in my own family, for example. And so that's in line with what was being suggested. You could listen to it and find out whether there is any evidence.
Actually, this was done. There's an article on does the Queen really speak the Queen's English?
Right.
And
which itself has changed.
But what was shown in the literature was that she did actually went along with some of the changes, and with some she didn't. And a question like that is, I mean, there's things like the U fronting where the U is pronounced more forward and so.
Echoing another thing that George was pointing to, did you look to see whether the same words cause errors? Do you make errors on the same words from beginning to end?
Before you answer the question, you can bring back to the phonetics. I mean, Ava is, can I say you're a phonetician or kind of?
Yeah.
So maybe she can say what she thought. Was there a qualitative difference over the years?
The one thing you pointed out with the dialect change or some sound changes, I couldn't pick up on that because it was just, I did listen to particular words over the years.
You did listen?
I did not.
What
I listened to was just the general impression of the speaking style and the way she was phrasing things and the way she read poems.
But this is really I mean, the Queen would be the best model for really someone that keeps it
Yes,
very...
but the opinion of what RP is and its social cachet has changed
Has
radically
changed
over the last
radically.
50 years.
Absolutely.
See, I come from New York City, and I have 5 brothers and sisters, and they've all gone different ways due to the fact that they've moved to other communities where New York English has different, what's the opposite of cachet? This takes place all over the place. In Germany, certainly after the war, in the United States. And those are things that you ought to look at anyway as possible sources. But they ought to show up in errors on the same or different words over time. Are the same words in error early and late if you have a large enough sample?
So what you suggest is some adaptation curves as a function of time would be, for a different word would not be this U-shaped, but would be more monotonic, you know. I mean, if you
I'm not sure, because I think if the change were taking place in dialect drift, it would be much harder to measure using word array as an index.
The study would be to check whether the trends in error rate have a underlying non-age related issue, namely that certain articulations have helped the recognizer over time or hurt it over time, and you could then try and subtract that out.
I suppose it's a pretty blunt instrument to look for that kind of an effect.
And there are a few words which I think she says Christmas in every speech.
Yeah.
And she probably says husband in every speech as well.
Yeah, well, I mean, not a big enough sample.
Family, yes. So maybe those are the words people use.
Yeah, we can. There's, by the way, also a nice story related to that, what she's saying, because we had, on some utterances, we really had problems and difficulties. So we asked that Eva to look into the development data, so because you should never listen to Eva. So, and she found that she's reading poems there. So,
and the error rates are high.
And then the error rates are high, So, and sometimes she's reading poems like a poem, so really with pronunciation. And sometimes she's just reading it like a normal text. So, and these things happen and you have to find out. So
What about out of vocabulary? Was that
that's not,
controlled?
that's
We
not
didn't.
a problem.
We
That's
put the word in.
We thought it is a problem, but it's not a problem. We have a very low OV rate.
So on a different tack, I wonder how reproducible some of these age prediction measurements are. And one experiment, which I don't know if the Florida database can give you, because my impression is they only record each person once.
Right.
But if you take some of the speaker identification data, you could age predict the same talker, same speaker, several times and see how close the age predictions are for the same person.
Yep.
And that would give you some insight into the...
Unfortunately, the age group where we expect age-related changes to take part is a little bit underrepresented in many of the corporations so far. I mean...
So you're saying that the age range, for example, of the speakers in the speaker ID database is too narrow, or an expanded range where you don't expect...
We didn't really see much of the... I mean, if you look at the Queen, it seems that with 60, 65 or so, she had an additional drop in F0, she had a decrease in the speaking rate, and that all happened around 65 to 70, around it. And with Alistair Cook, it was like 75, 80 where you saw the change. So if your data, show us a person between, let's say, 30 and 50, you have a 20-year period, but the changes are not, by far not as detectable. And so, and for most databases, this age group is strongly represented. So, I mean, if you want to do that with, taking speakers at certain ages, you need a large background database. Okay, so the background, I think, in any
I'm not even saying looking up and seeing how old these people are. I'm just saying we record Sanjeev, and we record him again a couple of weeks later, and we say predict his age. How close are the two?
Oh, okay.
Predictions on Sanjeev.
Actually, the fellow from Florida, in his talk, talked a little bit about this, that there is variability, for pathologies, because that they have some pathology actually, or if they get cold or something, and you come to speaker, it turns out they're recorded when he has a cold, he sounds or she sounds different. And so he was concerned about that in his data, in his database. And he may have some of that too.
So you mentioned the application of speech pathology, but at least in the U.S., much of the money in medicine is in cosmetic procedures, right? Would it be possible to build a device that in real time predicted how old someone sounded and could people learn to sound younger?
Okay, this is not a publication, so we're sitting here, so write a patent on that, and then we'll come.
Already there was this talk by Maureen. They talked about this implant that they are producing, to change the...
Yeah. We could just by just trying.
Meaning is just by feedback. So you talk to the system, it's telling you sound like
you need to modify your brain.
And then you train.
I like that.
It would be like a out of order feedback. You can take professional training, and definitely
could call it
You
the
have to
voice
like go
chip.
like whatever.
Actually, if we're going to do that, we may as well do it so that you can talk Chinese. If you don't, even if you don't talk Chinese, turn them off and then you begin to talk Chinese. You think in English? There you go.
That was good.
You know that Graybeard database, of course, is all telephone speech.
Yeah.
Which begs the question as to whether your M1 and your mass model for your thing will operate in telephone bandwidth. Now that's an experiment you can simulate very easily. That is to say,
Yes, that's a good.
telephone filter.
Yeah, just use a telephone channel. Yeah, that's a good suggestion. Yeah. And it's much more difficult. Like, you know, very often my son gets mixed up with me on the telephone, which would never happen without that reduced channel. I just, you know, people, you know, if they know me and my son answers the phone and then they talk to him and then he says, well, I think you want to talk to my father. And a lot of people have reported on that. And, you know, it's...
I really don't know what would happen with the cell phone. I mean, that's a whole other, when you start talking about GSM and all that.
Yeah, yeah.
It's an easy experiment to run too, but...
Yeah, you're right. Yeah, good suggestion.
More questions?
Hey,
Let's
everybody's
thank all our
introduction.
speakers once again.